Okay, good afternoon, everyone. So, welcome to the webinar on True Story Behind Morandi Bridge Collapse by Professor Calvi. It's my pleasure um, to introduce you all about IS Truckee. IS Truckee, as you might all be known, that it is a national apex body of structural engineers, and it is been established to cater for the overall professional needs of structural engineers. So, in order to achieve this objective, we regularly organize CPD programs, courses for the professionals, refresher course for the young scientists, students orientation programs, workshops, webinars, technical lectures, technical discussions, so that the knowledge is being disseminated to one and all. Uh, our, our professional body is mainly acts as a mouthpiece for the structural engineers, and also it licensed with the government bodies. And our members play a very important role in drafting the codes, drafting the new codes and writing the summary for the new codes, etc. So that's it about the association. And let me introduce the moderator of today's webinar, Mr. Alok Baumik. Alok Baumik is the current president of IS Truckee. He is the dynamic president of the organization and instrumental for organizing these webinars during the pandemic. Apart from being the president of IS Truckee, he is the managing director of a well-known consultancy firm, B&S Engineering Consultancy Private Limited. He has more than 40 years of design consultancy experience in transportation infrastructure. He is accredited as International Professional Engineer India and also a fellow of Indian National Academy of Engineering. He is an active member of several professional bodies such as IEI, CAI, IABSC, IS Truckee, etc. He is also a member of for drafting many codes for the IRC, BIS, etc. He received several awards in his professional career. The most recent one is the one awarded with SB Joshi Memorial Award for Excellence in Bridge and Structural Engineering. He has been lecturing as a guest lecturer in several institutions such as IAHE, VR, SES, DTU, IITR, etc. He has written more than 60 technical papers in various journals and presented more than 100 technical articles in various fora. He is also currently the chairman, editorial board of quarterly journal, Bridge and Structural Engineer, published by INGIA BSc. So with this, I hand over the platform to Mr. Alok Baumik. Yes, Mr. Alok Baumik.
Okay. Thank you, Dr. Visalakshi, for this nice presentation about my CV. And hello, everyone. Good morning to Professor Calvi. Good afternoon and good evening to one and all. I think we have people joining here from different time zones. We are very privileged today to have with us Professor Calvi, a very well-known structural engineer and a earthquake engineer, a very world figure. Just to give you a brief about this webinar, let me just mention that this is the second webinar that we are having on the subject of Morandi Bridge collapse. If you all recall, the first one we had in the month of October 2020, wherein I had delivered the lecture. And I had promised during that presentation. In fact, that lecture of mine was inspired by a technical paper written by Professor Calvi and his other teammates. in IABAC. And at that time, I had promised that I will one day get Professor Kalvi, the person who is so deeply involved in the study, research, and investigation of this bridge in our platform. And today I'm very happy to say that I have been able to keep my promise. We are all very privileged to have Professor Kalvi amongst us, and I wish to thank Professor Kalvi very much for accepting our request and to share his knowledge and wisdom. We are also joined today by an elite panel of experts who will be giving their insights after the presentation by Professor Kalvi. I take this opportunity to thank Mr. Amitabh Ghoshal, Professor Tandon, Mr. I.K. Pandey, and Dr. Harshavardhan Subbarao, who has joined as a panelist. I think Mr. I.K. Pandey will join later. He is currently not available, but during the course of the presentation, he will join. I will introduce the panelists only after the presentation is delivered by the speaker. Friends, collapse of Morandi Bridge has shook the bridge engineering fraternity all over the world. It is perhaps the first cable stayed bridge which failed catastrophically during this operation, during the service. 43 lives were lost. And this is not due to any natural disaster like earthquake or hurricane or cyclone, but the bridge collapsed reportedly due to a combination of factors which includes poor construction. Bridge was structural engineer Ricardo Morandi, who is perhaps one of the best engineer of the world in the 20th century, certainly the best in Italy, and one of the best in the world. The forensic structural engineering investigations carried out post the failure of this bridge is a repository of technical wealth, which is extremely educative, very informative, and should inspire not only the structural engineers but also all the stakeholders involved in this kind of infrastructure development project, be it the owner, the contractor, or the engineer. There are huge learnings from such disasters, though failures are not welcome, but in a way these type of failures provide a huge opportunity to learn and to amend our engineering practices. And that is why we are having webinars on bridge collapses quite frequently in our association. Friends, now I have the honor to introduce Professor Michel Calvi, the speaker of the day. Professor Calvi is the world leader in the field of earthquake engineering. He is professor at the University School for Advanced Studies Pavia in Italy, an adjunct professor at the North Carolina State University. He received a Master of Science from the University of California, Berkeley, a PhD from the Milano Politecnico, and an honorary doctorate from the University of Cuso Mendoza in Argentina. He has been the founder and director of Rose School in Pavia. This European School of Advanced Studies in Reduction of Seismic Risk was founded in 2000 with the aim of providing higher level education in the field of earthquake engineering. He is also founder and president of U Center Pavia, which is the European Center for Training and Research in Earthquake Engineering. It is the most powerful laboratory for earthquake engineering research in Europe, and about 110 research associates are working on this. He has been a member of the board of directors of GEM Foundation, which is a public-private endeavor, which is internationally recognized as a world center to bring knowledge, data, and resources for earthquake risk assessment worldwide together. He is one of the directors of the International Association of Earthquake Engineering. He has in his credit more than 250 publications and has authored two very popular books, Seismic Design and Retrofit of Bridges with Professor M. J. N. Priestley and F. Siebel, 1996, and also a book, a very popular book on displacement-based seismic design of structures with Priestley and Kowalski in 2007. He has been designer, consultant, or checker for hundreds of structural projects, including the famous Rio Atrio cable stayed bridge which is about 2,883 meters, which is in Greece. The Bolu Viaduct, 119 spans in Turkey, and the new housing system after the Aquila earthquake in 2009, with 185 buildings seismically isolated with more than 7,000 devices, which is completed in record 6 months' time. Construction of 100 of induced seismicity. He is associate editor of the Journal of Earthquake Engineering and has been invited keynote speakers in tens of conferences on earthquake engineering. He has been always active in conceptual innovation in seismic design, focusing on masonry in his early days, on bridges, displacement-based design,
I think somebody should call him on the phone.
Yeah, I think he's disappeared.
Now we have to call him.
1 minute, I'm calling him.
I think his net has been lost.
Hello?
Yeah, we can hear you. Hello.
Yes, yes. Hello.
Okay. I'm sorry. There was a reconnection. There was some technical hitch. So I was in the middle of, uh, you know, sort of talking about Professor Kalvi. I don't know where I lost my connection, but may I start again? Hello, am I audible?
think just the last sentence, whatever you were saying.
I think
Okay,
it's
okay.
enough. It's enough. You've been stating so many things. No
I
need
will
to
I will just conclude in about half a minute. So
Yes.
I was midway. I will just say that he has been an extremely active in various technical, programs all over the world. He has always been active in conceptual innovation in seismic design, focusing on masonry in his early days, on bridges, displacement-based design, and seismic isolation from the 90s. He is recipient of several awards, and one of that, which actually inspired me in giving the first webinar, was the paper, uh, uh, outstanding paper award he received from IABAC for the scientific paper Once Upon a Time in Italy, The Tale of Morandi Bridge. Apart from that, he is recipient of among many, the FIB Award for Outstanding Concrete Structures. He is recipient of honorary doctorate from the university that I mentioned earlier, awarded the Lamborghia per il Lavoro Milano 2010. And with that, I invite Professor Calvi to make this presentation. Over to you, sir.
Thank you. Thank you
Calvi.
for this. Thank you for this extended presentation. Probably the web was cutting you out because you were talking too much about me and everybody was bored. So I apologize because I only see 3 faces in front of me. I do not know how many people are listening. This is not what I was used for decades of conferences where it was a pleasure to read in the eyes of people whether they were bored or paying attention or whatever. This does not happen now. So it's like speaking by myself. Anyway, I'll try to do my best and I'll try to stay in about 1 hour or slightly more. I have been very curious about the collapse of this bridge. After its collapse in August 2008, I decided to start a small, but not so small, about 10 people research group to find out what happened without having any involvement with the Court of Justice. After a few months after the publication of some paper, I was forced to participate in the court case, and I had to shut up and not to talk anymore. And now it has just been, the court case has just been arrived at the phase where it is possible to speak again, because let's say that the phase of recognition of the evidence is finished. Now the court will go ahead probably for years, but there is not anymore any reason to be reserved about what has been found and happened. So I will try to talk about this bridge, about the context of the time, about the designer who was really, as has been anticipated, an outstanding person, and then to come and to try to find out what happened. This bridge was built, was conceived and conceived in the early 60s and completed in 67. It was a very, very special time for the construction of bridges and the construction of roads all over the world. In the US, it was signed in 56, the Federal Highway Act by President Eisenhower, that started the construction of the entire system of the federal highways, which is still today the backbone of the entire system of roads in the United States. And in the United States, in one single decade, they had been able to construct something like 30,000 kilometers of roads with an enormous amount of money spent. And what I'm showing is just a video that you can find in the web. It's I like very much to look at these very old videos and clips where somehow is a kind of a story of a time, of an era. In the US, this means that today they have a very high number of bridges that have aged and that can be in a difficult situation of maintenance. But if we look at what was happening same time in Europe and in Italy, at a different scale possibly, this is another video that I hope you see. Is in Italian, so don't pay too much attention, but it's for me it's extremely interesting. This is the video of the construction of what is called the Autostrada del Sole, which is the freeway that goes all the way from Milan way down to the south of Italy, that was also built between 56 and 64, crossing a lot of mountains. You see Italian engineers that are going to the US to see what they're doing there and to find it out and so on. And in this single freeway, there are 853 bridges and 572 overpasses. So you can imagine and look at this, what you see now. I mean, you see something which is an incredible way of construction for today. You don't do this kind of things anymore. But in Italy, we have a vast majority of the bridges that are aged. Nothing like this happened anymore. Well, there have been bridges, but not so many. And the same is true everywhere in Europe. In Germany, all the bridges were essentially bombed during the Second World War when the Allies entered Germany. And right after the war, they were reconstructed. So most bridges have been built at that time. So the 60s have been a great time for construction, but we are now in a situation, a lot of bridges in potential difficult situation of maintenance. If we continue looking at this, we should also recognize that the way of construction changed a lot. This person that you see on the screen is Riccardo Morandi, who is explaining how he conceived the bridge that collapsed. And he is explaining it in such a simple way that seems too simple from a certain point of view. But it is important to keep in mind that after the Second World War was the starting of post-tensioning, or pre-stressing also, of course. But the post-tensioning was known before, of course, but the availability of high-strength material was not so easy. The availability of high-strength steel was not so easy. And it was only after the Second World War that the main bridges passed from arch bridges, which probably in general were in the range of 60 to 80 meters or something like that of span. And after the war, they were still using this kind of construction, the one that came from earlier. And the Morandi bridge was a total exception. It was not common at all to have bridges spanning 200 meters. Actually, the only exception that we all know is the case of suspension bridges, the bridges that were built even significantly before the Second World War, with spans that were much longer than that, but these were still bridges, were something which were not usual. So Morandi designed this bridge in a very unusual way, something that no one had been doing before. And don't forget, at that time, structural software did not exist. So all the calculations were done by hand calculation. And some of the problems like fatigue or corrosion or time-dependent effect like creep fluage and so on, and strand relaxation were not so known. So Morandi was exceptional in doing that. And he also took a lot of risk. I recognize, we have to recognize that. He was a pioneer in this. And this is also one of the reasons why there was this tendency to design and construct structures which are essentially statically determinate to make them easier to be understood. In the 60s, there were not only a lot of bridges constructed, but it was also a time of big disasters. In 1960, there was the earthquake in Chile, magnitude 9.5, which is still probably the largest magnitude earthquake that has been recorded. In 63, there was the earthquake in Skopje, in Macedonia. And what was interesting there is that the first building isolated with rubber bearings was constructed. In 64, there was the earthquake in Alaska, magnitude 9.2, probably the largest one ever recorded in the North American continent. And not talking only about bridges, in 63, there was in Italy the disaster of the Vajont Dam. It was an entire mountain that collapsed inside the dam. The dam was an arch concrete dam and did not collapse. It stayed there, but there was a big wave that passed over the dam, and there were more than 2,000 people killed by the wave that went from the mountains all the way to the sea. This is just to try to put the things, at the time. And now a few words about bridge collapses. I think that probably all the people who are listening now have seen this video, which is very famous. This video is the collapse of the Tacoma Bridge, the one which is south of Seattle. I like to look often at this video, not because of the collapse, but to show to students what the structure could do before collapsing. You see, for me, what is incredible is that the bridge has not yet collapsed at this moment. This is interesting because this is one case of a bridge that collapsed essentially because of unexpected external actions. So something in this case, it was the wind, and it was a wind which was somehow inducing effects that were unknown. Unfortunately, this is a very unusual case because most of the cases in which bridges have been collapsed are not due to situations that were essentially unpredictable before collapse, but are due to deterioration, to increase of loading, to fatigue, and so on and so forth. And let me show you a couple of examples of this. One example is the Laval overpass in Quebec that collapsed in 2006, killing 5 people. After this collapse, there has been a lot of more studying on, particularly in Toronto, about shear problems in bridges and so on. And look at the video, which is on the bottom part of the screen. This is a very small overpass that collapsed in 2016 on a freeway not far away from where I'm now speaking. And if you see, this is just the failure of the Saddle Gerber that the Gerber saddle, which is taking the simple structure there. So this is something that probably could have been easily foreseen and even more easily strengthened before the collapse. And I could go ahead and show so many bridges where the problem is not something impossible. It's not a big earthquake. It's not a strange wind. It's not an unknown effect of von Karman vortices or so on and so forth, but just the fact the structures are not taken care a lot. Now let's go to this bridge. This bridge is very, very interesting. And the bridge, as you see in the top part of this slide, I'm not sure whether you can see my pointer, but anyway, you see that there are three main spans. And what Morandi was able to do was essentially to construct this bridge without interrupting the railway traffic, or without, there were all the main lines going from Milano to Genova. It's a very important one. And there was a river, and there were construction, and so on and so forth. So this construction, I will show you how it was doing something like this. Each one of these three spans, the one that collapsed it was called number 9, is the one that I'm trying to point now with the pointer. If you can see it, it's close to the river, and it's built with. It's now you see it in a red oval, and it's built by a pier. The pier was constructed in a rather traditional way, as I will show you. But then there is a tower, an antenna, and this antenna is not touching the deck. The deck is supported, as I will show you, only in 4 points. The deck is very heavy. It's 4.5 meters deep, and it's essentially very strong in flexure. And there are 4 transverse link girders. So these are the points where the deck is supported, 2 on this side, the one I am showing in the slide, 2 on the other side. And there are only 4 cable stays at an angle of about 30 degrees. In addition, here at the end of the main span of the deck, there are 2 simply supported Gerber spans, 36 meters long. And they have been used by Morandi also to be able to adjust for small displacements and so on. So to make the bridge more capable of adjusting, because there could be relative movements between the different main piers. If we look at how the bridge was constructed, we will see that the construction process was traditional for pier and antenna. With small construction site. You see in the slide, you see houses, you see a train passing by. They were constructing in the middle. So they were going to the top of the antenna in a traditional way. But then you look here, what happens from this point on, they are constructing the main viaduct with what we today would call a segmental construction. Each one of these parts was about 5.5 meters, and they were not sustained with internal cable, but with external cables. You can see the cables up here. So these cables, you see here, there is a saddle. So the cable here is about 2 meters higher than the deck, and then these cables are going down, and there are no added as long as he goes ahead with more segments. And you see when he is the end of his construction, the cables are not working at all. You have these temporary strainers that are passing here and then are inclined and going down here and taking care of putting horizontal compression and to give enough bending capacity. It's only at this stage that he was connecting the structure to the main cables. You can see them here, and we need to spend 1 minute on this, because this was probably the most original point of Morandi design. He was using main cables, this down here, and they were connected to the girder, to the viaduct. Then he was casting some concrete around these main cables, And he was using these secondary cables that you see are not connected at all, only to be able to put in compression the concrete. Only when everything was finished, he connected the concrete to the viaduct. So this means that there was an internal action in such a way that the concrete was compressed by the secondary cable. And at this stage, when he was adding the live loads and so on, the live loads were somehow inducing only some decompression into the concrete without arriving to a cracking situation. So the stiffness of the two main cables was the stiffness of a full section of about 1 meter by 1.2 meters. So they were extremely rigid. So this means that there were small displacement, which was an advantage. There was no cracking because the concrete was compressed, and so on and so forth. Clearly, as you can see in this slide, the construction process was not that accurate, because you see that instead of having a continuous viaduct from the top to the bottom, this person here is just closing in some way the viaducts. So this will make an easier way for corrosion and water penetration. Anyway, the post-compression is taking place in concrete. The ducts are injected, and only at this stage, you see this is concrete now, and at this stage, the Gerber 36-meter span was added, and this was prefabricated beams, again something which was very unusual for the time. So you need to pass on the bridge to be able to locate the prefabricated beams at their place. But again, he was able to do all this without any interaction with what was happening at the bottom of the bridge. You should consider that to locate this before or after having completed the secondary cable make a difference, because if you put it before, this is not reducing the compression in the concrete. If you're putting it after, it's reducing the compression in the concrete. Now, this is an image, a beautiful image of the bridge completed, which was a masterpiece. It went on all the possible journals and so on and so forth. But now let's have a look in some more critical way. Alok was mentioning the Rion Bridge. This is the Rion Bridge. You can see down here a comparison in almost a true scale of the section of the Morandi Bridge and the section of a modern cable stay bridge. The weight of this is much larger, which means that this is inducing a lot more compression. In fact, the span here is 560 meters, and the span in the Morandi Bridge is 200 meters. The other thing that is immediately clear is that here, this bridge is very redundant. Actually, in a cable stay bridge like this, we normally design even considering the possible failure of one or two cables due to the possible impact with a small plane or so on, and the bridge should be able to resist. In the case of the Morandi Bridge, the bridge was almost statically determined. Let's have a look in more detail in how the bridge was designed. Morandi had a patent on his own system for post-tensioning, and you can see this drawing here is taken from his patent. What comes to immediately comes to be noticed is that the density of the cables very difficult to inject the cables. It was very difficult because the material for the injections were not as good as those as today. They were less fluid, and the space between the duct and the steel was much less. So this gives some hint about the possibility that the injection was not done in the perfect way. But if you look at the cable, very different from the cables we use today. So Morandi was able to work at about 1000 MPa in his steel strands. The other thing that you immediately see, this half of the viaduct of the deck. And you can see that, okay, there is some distributed steel, which is very minor. But if you look at the main steel, you have some post-tensioning cable here. And you know why? Where the cable is coming down. And you have some post-tensioning here where you are supporting the deck from below. And you have some cable here. There are even regions like this one here where there is no post-tensioning. And you know why? Because he was counting on the compression that was coming into the deck because of the tensile force in the strand. So you should imagine that you have this force here, this diagonal force here, and here in the deck. There were, as I was saying, the transverse link girder, this one here, the red arrows, and there were the cable stays. The cable stays were made with 352 main cables, 1.5 inch diameter, and excuse me, 464 main cables, and 352 were the main one, and 112 were those used to post tension to put into compression the concrete. And look at the force induced by the weight was inducing a tensile force in the cable of about 12 meganewton, and the force induced by dead load was more than 10 meganewton, but the force induced by the maximum conceived live load was only. What I'm trying to say is that this bridge is a very heavy bridge, and the variation of forces induced by live load is very small with respect to the forces that are there because of the self-weight and dead load. This means that, in fact, the dead load and the live load was only able to force in the concrete of the cable, so that there was no possibility of any extended and systematic cracking in the diagonal tendons. But as I was saying, we may suspect that the injection was not that good. But if we think in terms of capacity, the fact that there is not injection does not make a big difference. You know, the system is working the same way. The capacity is the same. So the direct effect on a potential failure of the fact that the cable are injected or not is very minor. If we talk about the potential for corrosion, is another story. We will talk about that. I mean, the fact that water, moisture, and so on can penetrate and enter and travel along the duct can favor corrosion. But if there is no corrosion, there is no problem. So if we go ahead and we look into the supported beams look very much like a traditional simply supported beam of today. You see here the distribution of the cables. You see that there are 6 of these prefabricated beams with a variable section. So the one on the right is the mid-span section. The one to the left is a section close to the support. Again, these were pre-stressed, and again, there was no problem in this one. Now we have to spend 1 minute in looking into what happens over the years. Morandi himself started being worried when he was still alive, because there were, people noted that there were some cracks that were not foreseen and so on and so forth. So he was worried. And actually, I focus here on one intervention because in 1 hour there's not enough time to discuss everything. In the early 90s, it was decided to strengthen one of the 3 main piers. And the reason why you find the justification that they strengthened the Pier 11 is that they found a lot more corrosion in Pier 11 than in Pier 10 and 9. 9 is the one that now collapsed. So you can see that in Pier 10, they decided to replace completely the tendons of the pier. And in Pier 10, they did some strengthening only at the top. In Pier 11, they only added some protection to reduce the possibility of water to enter. And strange enough, you can see in what they wrote in those years, they were foreseeing a limit condition for corrosion in the year 2030. So probably this is the beginning of the process that was concluded in 2018 with the collapse. It was clear to the people that you look here, there were problems of injection. You see here, this is a situation, they removed some of the concrete and this was the situation of the cable. And they reported that there might have been some loss of post-tensioning. And you see in this slide here, you see, okay, the Pier 9 is not there anymore because this slide has been taken after the collapse. Pier 10 is here without any evident strengthening, and Pier 11 is in the background, and you see that the cables have been completely replaced, or at least you can intuitively see that there is something different. Now, the next step when we started looking into this was to try to estimate the member capacity and to see whether the design of the time was similar to what we have been doing today. So we look into a number of problems, it was clear that there was some deterioration of the stay strengths, that we have to look if this was relevant or not. There might have been some elongation of the stay cables because of this deterioration, and this might have favored some shear strength problem in the deck, which was, as you remember, very stiff also from the point of view of bending. There might have been some local failure in some part of the deck. There might have been some shear failure in the simply supported span. We started to investigate all these potential problems without having any real insight in the debris remained after the collapse. So we used the SAP 2000, we used the MIDAS, we used the OpenSeas, we used the Seismostract, we used the applied element method. I will show you something of all this. But let's have, first of all, a very simple look. You see here a modern, simple model, elastic model of the three main span. And you see that the results that we obtain are very similar to those of Morandi. And actually, the capacity of the stays was much higher than the demand. Actually, one of the strengths was capable of taking more than 40 meganewtons, so more than 2 times the actual tensile force. And from the point of view of bending and shear capacity, even if you remove the stay, the other one is capable of taking the entire force. But there are problems that I will show in a minute. We also did some seismic analysis to see what was the dynamic response of the bridge, and we found that for the seismicity of the location, the bridge was essentially fine. I mean, with some small problems, but let's say that a seismic strengthening would not have need any relevant, costly and difficult intervention. So if you see here in the bottom part of the slide, you have an indication of what is the action in terms of bending, and the capacity is in gray. You say that the points showing the capacity, 0.1, 0.3, 0.2, are much larger than the maximum possible demand, even including a seismic event. And the capacity is calculating using a complete nonlinear analysis. And if we look at what happens in terms of shear, something similar happens. The capacity is much larger. The capacity in the deck is much larger than the demand. No problem at all. No problem. And we apply the modified compression field theory, and you find that there is no problem. Of course, when you removed one of the cable and see what happens, in terms of axial force in the cable, there is not much different. But in terms of the horizontal bending moment, the moment in the plane of the deck, you have a large bending moment because the deck is now supported on one side only. So you have a deck that can rotate in its own plane, and of course you have a lot of torsional demand because you are supporting the cable on one side only. And if you now look at the torsional demand and capacity using the variable angle truss model, you find that the demand could be larger than the capacity. So what I'm trying to tell you is that if you remove one stay, you can have a shear torsional failure in the deck because of the in-plane bending moment and because of the torsional applied moment. So we could conclude this saying that if you have a problem in one of the states, you can have a problem in the deck and everything could collapse. This is somehow a temporary conclusion. We will go ahead on this to say, okay, this the collapse might have been originated by a problem in a state and then continuing in all what happens. What could have been inducing the problem in the state? Well, it could have been a deterioration due to corrosion. It could have been a fatigue problem. It could be a combination of these two. It could be also an exceptional load that we will discuss in a minute. So have a look into this, and we now use a very advanced modeling. This model uses a software which is extremely expensive, and is a model that we developed with more than 500,000 degrees of freedom. This kind of software is made by small, completely rigid parts connected one to each other by deformable elements. And in connecting the small parts, we were representing each single rebar, each single cable, and so on and so forth. You model all this, and you come out, and first of all, you check and compare the results of this modeling with other kind of modeling, and then you see what happens. And for example, you see what happens if you increase corrosion, if you reduce the section. And you see that to arrive to a collapse by reducing the section of the cables, you need some 70% reduction of the section of the tendons. You need an extremely advanced state of corrosion. If you have, say, 50–60% corrosion reduction of the section, you have a large displacement. But if you have this large displacement, someone would have been reporting an half-meter displacement of the deck. So there is something that is not convincing us. And what happens if you have an impulsive load? Why an impulsive load is of interesting? Because right at the time of the collapse, there was a track with a big steel coil on his transporting a big steel coil. And it might have happened that the steel coil was falling from the track to the deck. Now, what is the capacity then? And we analyze this, and if we take only one of the beams of the simply supported spans, you see that with a point load of about 650 kilonewton, you have a collapse like this. If you consider the entire grid, the load increases to 800, and you see, but of course you need to have the coil that drops exactly right there. If you also add the slab on top, then you need more than 3 meganewton point load to induce this kind of local collapse. The total weight of the coils was approximately 30 tons, so it was about 300, not 3,000. But if you include the dynamic amplification, it could be compatible with something like that. But then, is this inducing a total collapse of the bridge? The answer is no. In the sense that we modeled the possibility of having the failure of the simply supported span. You have the bridge that oscillates like this, but then it stays again. And you can see this in this slide. It goes up and down, and then it stops. So if you have a point load, an impulsive load collapsing there, you may induce the collapse of the simply supported span, but it's difficult to induce the complete collapse of the bridge because of that. As we will see later, actually, this can be a possible, say, trigger of the collapse, but not because of the collapse of the simply supported span, but because of the increased tensile load in the cable, in the stay. If this adds up to a certain level of corrosion, this could be the trigger. We will see it in a minute. Now, our conclusion, again, temporary conclusion, is that we might have had a collapse at one of the stays, at one of the stays at the top there or at the bottom here, and this might have been inducing the collapse of the entire bridge. And what we did was to look into this problem, and to I will show you a video clip in a minute. These are just single shot screen taken from this video that I will show in a minute. This is at 2 seconds. So the trigger point now is to release the top of one of the stays here and see what happens. And at 2 seconds, you have that this is released, this starts moving that way, this other cable is released, and then you start having the shear torsional failure that I was discussing earlier. In 4 seconds, you start having pieces that are falling on the ground. You see that you have rotation of pieces like you see at 4 seconds here. I hope you can see my cursor. If you have it here, you see that this is rotating, this is rotating. Why is this important? Because to see whether this reconstruction is faithful or not, one of the evidence that we could use is the location on the ground of the different paths of the real bridge, and to see whether the final location of the paths of the bridge of our model is consistent with the location of the location and rotation and so on of the different parts of the bridge. So you can see now this is I stopped it. Let me. Okay, you can see the video. I think this video was done more than 1 year ago. I will show you something else later on. I insist on this because there was no evidence of anything. We did this just using our capacity of analysis. And you can see that you have a certain distribution of the different parts of the bridge on the ground. And so this is exactly what we check next. And you can see top and bottom. These are photographs taken on the place, and these are distribution obtained from the analysis. And you see that there is already some significant correspondence between what you can see in the field and what you can find out of a model like this, which is a model, I repeat, with 500,000 degrees of freedom, where the only point that you start is to break up the one of the stays, and all the rest comes from physics. So this is what I'm trying to say is that there cannot be any measure of forcing something to go to one place or to another with a 500,000 degrees of freedom model. And these are other comparisons. And this is something that was published more than 1 year ago, and I think, well, more than 1 year ago for sure. And is that paper that Alok was referring to that got some recognition. Now, at this stage, we are only able to state that all original elements had ample margins of safety. Variable live loads have little influence. Live load cannot have been the trigger of the failure. A progressing reduction of the steel section and the concrete compression in a stay would result in large increased displacement before collapse. And an exceptional point load can induce a local failure, but is unlikely to extend into global collapse due to this local failure. We found that the bridge was essentially fine, and we concluded that essay saying that the loss of one stay could be the final cause of collapse, and the possible initial cause could have been some possible corrosion fatigue or possible combination with the section point load. This was done before having any access to the evidence. Now I will tell you something that I've not presented everywhere anytime, not published yet, that comes from evidence coming from the court case. And now I will do this in about 15 minutes, so I'll try to stay in this hour. Of course, these 15 minutes could easily become 2 or 3 hours if I should enter into all the details now I know. But the first point that came out of the material available of the course was a video, which was made secret before. And I'll show you the video now. You can see the video. This was taken by chance by a camera which was in a construction site nearby. I will show you again this video just to comment on it. But this was very fortunate, as you can see, because as you can see, it is possible to see almost everything. So now have a look and I'll stop it. Stop it now. Nothing happens yet. I'm sorry, this is not what I wanted to do. Let me go here again. Okay, see, look here, look at the antenna. The antenna here is already broken, and the upper part, the upper L of the antenna is falling towards the camera. This means, even if you cannot see it, that this cable down here, which is the southeast, so is on the side of the sea and is towards Genoa, towards not towards France, towards Italy, let's say. It must have been failed. This failure is only possible because this part here has lost completely its capacity, and this cable here has been taking this part in towards me, towards the audience, towards who is looking now. You see that coming, this part is falling this direction, and immediately afterwards you see that now also here is falling. But look at the deck on the other side. You see that the deck on the other side is much more advanced in its collapse than the deck on this side. So there are a couple of seconds, probably 1, 2, 3 seconds difference, in the sense that this part of the deck has collapsed first because of the release of this cable. Then this part has started collapsing, and then this deck starts collapsing. Let's go ahead. You see, this deck is already down there. This cable is not there anymore. You see that there is no cable here. This upper part is collapsing. Now, I think this should be enough. I think that, well, if you need more insight, you ask me, and I will run again this in the brief discussion we're going to have with the panelists afterward. So let's go one step ahead. Now we know that this is the reality, and now we know that what we were guessing was essentially correct. And we now know that it is that specific cable, the one that is southeast. So look at our model. Look at our model. You look at this. Look at the figure which is on the bottom right part, and you see that you have this cable which is taking this part of the upper antenna, and then this cable is failing. Or you can look at this. These are oriented in a different ways, but I understand. So this, let me say that this is what happens first is to the left. So you see the failure of the cable, the upper part of the antenna is released, and then you go to the right side, and you see that you have a progress, and I think you can look at compare the bottom right image to the one which is in the shot screen of the video on the top, and you see that this is very, very similar. Or you can see, of course, when we're dealing with a model, we can rotate this as we wish. So you can see in the upper right corner that we have another image of what happens in the screen, and probably, well, not probably, What we try to do there is try to put the same point of observation. So you see that with essentially no adjustment, our model was exactly reproducing what happened in reality. The only problem was to start the collapse on the right cable and nothing else. So we were a lot reassured about the quality of our model. But what we did next then is to explore two issues that I will be briefly discussing in the next 5 minutes. And these two issues is, okay, now we know that the collapse has been initiated at the top of the southeast state. Why? What was the level of corrosion there? And what was the increase of load there? And you can see here in this screen, you can see a little blue item on eating the deck in the two bottom figures. This blue item is a coil of about 30 tons. And we were able to have a lot of insight into the speed and acceleration of the truck which was passing on the bridge. There is no evidence, there is no sure evidence that the coil collapsed. The coil the coil fell down from the truck. There is no evidence that give us reassurance about that. But the question is, if the coil failed, if the coil collapsed from the truck into the deck, would have been enough to induce the collapse? Well, the answer will come in the next slide, but the answer is yes, in the sense that if it was collapsing in a region which was close enough to the cable, the increase in the tensile force in the cable would have been enough to induce that increase that was passing from safety to failure. This is possible only if the situation of the top part of the cable is deteriorated enough, because otherwise there is no way. So let's have a look into this. First of all, you see here a reproduction. You see in the upper right image, you see the truck, you see the coil that in this reconstruction has fallen from the truck and has hit the deck, and you see a reconstruction of what might have been happening. These reconstructions are consistent with our model in the assumption that the coil falls down there. But to obtain this, and this is something we should spend some moments, but to obtain this, we have to have a look into the situation of the top part of the southeast state. And these are some of the parts. I could show you hundreds of slides, but I selected only 3 to show you some main issues. You see, these are part of the remaining debris. So we've been able to cut through. This was the top part of the antenna. You can see it here. This is the antenna. Look at if you don't see my cursor, I am pointing to the upper right image, where on the left part you see the antenna, and coming down point towards the, say, the middle side of the screen, you can see the cable. This part of the debris was there, and it was possible to cut it in different ways and to see the situation. And the situation was very peculiar for several reasons. One reason, in the upper 2 meters, there was not the duct. So the cables essentially were just simply into the concrete. This means that, and we have been producing a lot of very detailed models on this, there was an internal micro-cracking due to the anchoring of these cables. This internal micro-cracking could have been favoring the moisture and water and so on penetration into the cables. A second big point is that there were large voids found around the cables in the region about 2 meters from the connection. So imagine that you have the upper part, which is not in cables, it cannot move, is anchored. It open micro cracks, and then down a little bit more, you have some half-meter void or something like that. So you have penetration, you can have penetration of moisture, you can have presence of water, you can have a localized corrosion. In other sections, there was very little corrosion found. So this gives also us an explanation why there was not a significant elongation of entire cables. It was a localized problem. That region was weaker, and that region was weaker because of several local problems. And you see here a third important issue. This third important issue is that during the construction, they were not very careful in the proper location of cables. You have there a comparison of what was designed and of one of the section cut through, and look at the distribution of cables. So the cables were somehow packed together. And if you have some moisture and entrance, you can have all sorts of, I'm not an expert of corrosion, I've seen the work of others on this, but you can favor a lot the progression of corrosion in a localized part. So now the situation is more clear. What could have happened is that you have a local loss of capacity, and then you might have had the falling of the coil with the instant increase up there, exactly where you have an unknown reduction of strength. And you look at this, this is another section cut through. Look at the distribution. What you see in red here, this point here, are the main cables. What you see in blue, what you see blue here, are the secondary cables, those that were used, all these blue points, used to post-tension the stay. And what you see here in green is just ordinary reinforcement. And what you see in the right part of the slide is just one case to give you an idea of a comparison of the original capacity of the section. So you see the original design capacity of the section is in blue, is the outer part here. Because of the different geometry, the capacity was in black. You see the capacity here, it's not symmetric anymore. In general, is even favorable just because of a chance, because when you have an increase in bending moment, normally you have when you have an increase in tension, you also have an increase in bending moment, and you're going somewhere in this direction. But if you include the local level of corrosion in a very detailed model where you put all the cables in the right position, you see the model in the bottom part of the slide, then the resisting moment axial force capacity is described by the red line. So you see that you have a decrease of capacity of essentially 2 times. You go to 50% or something like that. And this is with the corrosion level that was detected locally. So you have a cable that is in relatively good condition in all its length, but relatively good condition. You can have 10% corrosion deterioration, but you have a capacity which is 2-3 times what you need. But locally, you have a significant reduction of capacity, and then all of a sudden you have an impulse load that induces a collapse. So this is today our reconstruction. Of course, this will be the object of a lot of discussion in court and so on, but we are going to publish in the next 6 months probably 5 or 6 papers related to all the details, all the dynamic testing, all whatever. I'm now giving you an hint of what's happening, but of course, as you can imagine, We have produced several reports on this. This is the end of my presentation. I thank you. I've been staying almost exactly in 1 hour, so that we can now have some half an hour or so for discussion. I hope you enjoyed it. I don't know. Maybe the organizers can check how many people have abandoned the presentation, and this is a good way to see whether it has been interesting or not. And I'm here happy to interact with you.
Thank you very much, Professor Calvi, for such an excellent, fascinating presentation on the collapse of Morandi Bridge. In fact, this is, I think, this is just a classic example or a textbook style presentation of how a forensic structural engineering investigation is to be done. Perhaps a considerable amount of lessons needs to be learned by all those who are little involved in forensic investigation in our country. The extent of skill, knowledge, in-depth exercise that is required in any forensic investigation, this is just a glimpse of that. Thank you very much. We will now introduce our panelists. We have 4 elite panelists with us. And then we will initiate some question and answer on this. We have with us Mr. Amitabh Ghoshal. He is the doyen of structural engineering fraternity in India. And I can tell you he's one of the big pillar of the industry holding the edifice of structural engineering fraternity in our country. He is presently the chief advisor to the board of directors Stoop Consultants. He is the immediate past president of Consulting Engineers Association of India. And he has a very extensive experience in the management of design office with large manpower. He was involved with, or is still involved with Stoop Consultants Limited, one of the giants in India in terms of consulting. And may I now request Mr. Ghoshal to give his remarks on this beautiful presentation.
Well, there are more than 200 participants, and I am sure everybody is inching to ask questions. And so I will not waste time in complimenting on this fascinating and mind-boggling presentation which has been done. This will be done again and again. I have 2 simple questions. You see, the failure has happened. Now, what could have prevented the failure if we think in that terms? You see, for future learners, one is today we are able to put sensors in various parts of a structure. If sensors were available, or today if we are building a bridge, and if we decide to put sensors in cable-stayed bridges, what would be the right positions, or what would be the extent of sensors that we can have, and how to monitor with them? Because today we have some tool for understanding how a structure is behaving, which was earlier left to only guesswork and to somebody's understanding of a structure. Now, that is my question 1, that how can sensors help? The second question is more administrative, I would say. In various countries, there are various route taken for the maintenance of a structure or absence of maintenance. I will say in many countries, there is absence of maintenance altogether. Now, but there are countries which have introduced systems like in USA, and understand that there are large consulting firms which are given tasks of maintaining major bridges, like Steinman or TY Lean. Such companies have been given responsibility for maintaining and looking after certain bridges. In certain other countries, there is routine maintenance. There is a team introduced who will go with a manual. They will go point by point. Now, with your insight and with your exposure to this analysis, this particular bridge analysis and all that, have you been able to form an opinion what would be the best way to save our valuable assets? You know, a bridge collapse does not mean collapse of a bridge. It means collapse of a complete transport route and confidence of the engineers, which is much more serious than what we think. I will conclude my questions here. Over to Mr. Bhowmick and of course to Professor Kalvi.
So, Professor Kalvi, how is this? Can the instrumentation and new technology help us to reduce the uncertainties? That's the question, I think, what Mr. Ghoshal is asking.
I think I've appreciated these questions and this discussion. You have been really pointing to some of the crucial points for this bridge and in general. So let me try to answer first with the reference to this bridge. I strongly believe that that problem of a local defect at the top of the stay would have been extremely difficult to be detected with any kind of sensor. Actually, in 2015, 16, 17, on this bridge, there have been some quite complex dynamic identification tests, locating accelerograms in several points of the stays of the antenna and of the deck. And essentially, I examined them in a lot of detail, and it was impossible to detect from this dynamic measure that specific problem. I think I know quite well that kind of measures, and I can comment on those. I know much less about measurements made about corrosion in a cable through electric measurements and so on. That's not my field. But I have learned, listened to other people that also through those measurements, they would have not been able to find that specific problems because it was not, I mean, the differences were not good enough to detect that. So, in general, I think that we should discuss the problem of sensoring, monitoring, and so on, like good engineers as we are, and probably all the audience are. I don't think that sensoring, monitoring is the solution of everything. Is a good instrument. Is something that we should make a use of. But what I continuously repeat is, please don't put a lot of instruments to measure different quantities just because you do not know what to measure. Don't put instruments, try to get as many data as you can, and then you will interpret the data. Please do exactly the opposite. Please have a model, find out what could be critical in your structure, and measure what could be critical. This is the only intelligent way, in my opinion, of doing that we should convince the authorities. This is not what is done in my country. You know, authorities, I'm mixing your first and second question. Authorities, you know, people who are decision makers are believing that they put sensors and they have solved their problems. They protect themselves. This is not true, because you are measuring, if you are measuring things that do not have any influence on the true parameters of the structure, you are measuring nothing. So my next point is that I believe that monitoring should come out from designing, not the opposite. So for a new structure, the sensoring should be part of the design of the structure. The evaluation of limits should be part of the design of the structure. I'm talking about important structures. I realize we cannot do it for something which is very minor, But for important structures, this is what we should do. I mean to say, look, these are the problems that could happen. And this has to be measured. For an existing structure, is exactly the same. There should be an assessment first, design of sensoring, and decision to be taken. And if a structure is in such bad conditions that there is that monitoring is a waste of money, don't spend money in monitoring. Strengthen the structure and design the monitoring on the structure that has been strengthened, not on the structure as it is. This is my point of view. For what concerns that bridge, the void I was talking about was approximately 30 to 50 centimeters inside the concrete. Again, X-ray is not my area, but I've learned that it would have been impossible to take X-rays up there. Probably would have been killing the operators because of the presence of X-rays in the opposite direction and so on and so forth. So I am in the opinion that it would have been impossible to find that defect. But on the other side, let me very frankly state here, and this is something I will not repeat in court, that I wonder why, if they have been strengthening one of the three antennas, one of the three systems in 1990, we had to wait 30 years to take care of the other two. This is not because we found a defect, but I found that there is something irrational in this. I hope Professor Ghoshal, I answered your questions.
Well, you have emphasized on one point that the designer should be, for a major bridge, should really try to educate what are the points to take care of. I mean, making a bridge maintenance manual should be part of the responsibility of the designer. That's a very important lesson I take from this. Thank you.
Yeah, I mean, understanding of the response of structure and behavior of the structure is much, much more important than using the new gadgets and instrumentation for getting the behavior. I mean, I think that seems to be the trend nowadays. Okay, so we have now, I would like to introduce our second panelist, Professor Mahesh Tandon. He is the Managing Director of Tandon Consultants Private Limited, and he is the past president of our association, that is IES Trucktee. He is another pillar in the structural engineering fraternity, and he has accreditation of International Professional Engineer. He is also a fellow of National Academy of Engineering. Professor Tandon, your remarks, sir.
Yeah. Thank you. Can you hear me?
Yes, yes, loud and clear.
Okay. So, good evening to everybody. And what a pleasure it was to participate in the excellent presentation made by Professor Kalvi. What we have learned is that failures really are our best teachers. That's what I can say after listening to this presentation. And I would like to ask the question upfront before I go any further. I think back then, when this bridge was constructed, engineers didn't really think in terms of durability. Also, disproportionate collapse, or the lack of indeterminacy in a structure and what importance it holds, never really occurred to engineers at that time. If it did occur, I think it was probably somebody who was more senior who said, hold on, I mean, let us do the design first. And this is these are my two conclusions. And I would like, of course, Professor Kalvi to respond to whether I have come to the correct conclusion that these were the two reasons why this collapse took place. But before he answers the question, I would like to say a few words about engineer Ricardo Morandi, who inspired a generation of structural engineers by his bold designs. I was one of those engineers, and that's why I can talk about it. I think that during, let's say, the middle of the 20th century, there were some great concrete bridge engineers. Eugene Freyssinet from France, Jean Muller from France, Fritz Leonhard from Germany, and Riccardo Morandi from Italy. I think these were the four names that stood out at the time that I was really involved in major bridge designs in a big way, and designs which were perhaps beyond the experience that I had at that stage. I got inspired by another twin of this bridge in Genoa. It is located in Venezuela in Maracaibo. It has more or less the same design. It's a twin. And it was constructed a few years earlier. When I was designing the world record concrete cantilever roof structure for the aircrafts in Mumbai, aircraft hangar in Mumbai, I really got inspired by this single post-tensioned hanger or stay, whatever you want to call it, by the bridge. Even to me at that stage, it did not occur that this does not have enough indeterminacy. But I applied it nevertheless, and I am glad to say that after this was designed in the late 60s, so we are talking about some 40, 50 years later, it's still standing. It's in good shape, and it's still housing the aircrafts for which it was designed for. I don't know whether that world record is broken or not, but because I lost touch in long span roofs and got into bridges. But really speaking, the inspiration came from Professor Morandi's bridge in Maracaibo. So that's all I wish to say. And except, of course, that one person who made a remark about him is still something which is embedded in my memory. This is one of his peers who said that he was an engineer with an incredible creativity and was the greatest Italian bridge designer we ever had. These are the comments that were made about Dr. Morandi. So I think that we have to look at not the collapse. It could have happened because of the time that it was designed and built, but we have to think of what contribution he has made in the field of bridge engineering and structural engineering, because I used his concept not in bridges, but in a cantilever roof hanger. So now I think I can yield to Professor Calvi and ask him to or request him to please comment on the two conclusions that I have reached in this presentation that he has made.
Thanks, Professor Tendon. My answer and reply could be very short, simply stating I agree, and that's it. But let me elaborate only slightly more. Riccardo Morandi was clearly an outstanding engineer. There's no doubt about that. And on this, I would like to make two comments. One is that in this case, in the case of this bridge, Riccardo Morandi was the designer, but he had little control on the construction. And the main problem that I think are coming out very clearly are not related to design, are related to construction. He prescribed that the ducts containing the cables were continuous, so they should have been inserting the cables before and then locate the ducts. But what they did was to cut entirely the ducts and locate the cable inside the ducts and then to close it in some way. This is just the fact that there are these big voids, these big holes on top is something due to construction. The other only, so this is certainly a problem. And this is something that we should also take as a lesson. You know, often bridges and structures are not constructed exactly as they were conceived. He was prescribing a certain timing of occurrence between different operations, and this timing were not followed. Actually, there were issues where he prescribed 90 days that were reduced to 3 days. As I was saying, they needed to have the construction to move the prefabricated beams. So they loaded so I don't want to elaborate more, but you understand what I mean. The other point is that the only comment I have on the first things you mentioned is that that was also the time when concrete was considered perfect and eternal or something like that. You know, this is not Morandi or Freycinet or Zorzi. You know, concrete was considered to be the solution. Now we know that concrete also needs maintenance, that concrete is not, that carbonation was not known at that time. The fact that there could be an effect that will eliminate the passive protection of concrete to steel was not known. This is also part of the entire issue. But I believe that the main problem has been that there have been very clear construction defects. That these defects were extremely difficult to be detected, as we discussed earlier. And then we could say that. But I agree on the fact that most of what I've been discussing was essentially not known in the early 60s.
Thank you.
Thank you, Professor Calvi. I was just wondering, this Morandi bridge was one of the unique bridge at that time of construction, even today. And it is designed by a person who was a legendary figure at that point of time also, because Professor Morandi was very, very famous after the Maracaibo Bridge at Venezuela at that time. Now, when you have a bridge of, a sort of an iconic bridge like this Genoa Bridge, why he was not involved during the construction is little surprising to me. Any comment, Professor Calvi?
The reason is very simple and is very common. He was not working for the authority who was paying for the bridge. He was working for the construction company. So there was a call for bid. He worked for the construction company. They got the project, and then the construction company decided to go ahead in the construction without needing him. That's it. So he was not hired by the Federal Highway Administration or whatever. He was hired by the construction company. That's it.
Okay. Thank you. So now we have our third panelist, Dr. Harshavardhan Subarao. He is the chairman and managing director of a leading consulting firm, namely Construma Consultancy. He holds a PhD from Imperial College London. He is a governing council member of our association and vice president of YAPSE, Zurich. He is member of YAPSE Task Group 5.1, which is on forensic engineering, and Task Group 1.5, which is international database of bridge failures, and also a member of the editorial board of Forensic Engineering Journal of ICE UK. He carries the legacy of his legendary father, Dr. T.N. Subarao, who is very well known, I think, in the international fraternity as well. Over to you, Dr. Subarao.
Thanks, Alok, for those kind words. Professor Calvi, that was an outstanding presentation, I would say, and we're so beholden to you for sharing the secret at last. You know, the paper in 2019 left a little unsaid it left a little doubt as to the matter of corrosion, the behavior at the top of the cable, and it kept that in reserve. But now you've given us the facts, and you've shown us how the void at the top and the durability phenomena, which wasn't adequately addressed, and the fact that it largely went undetected over so much time was one of the triggers that started the collapse. Maybe also concomitant with the falling of the 30-ton coil, the impact load created, and the tension that accrues to that south side cable south side stay, I think the southwest stay, and thereafter the breaking at the top and the whole mechanism, which you so beautifully brought out with this AEM method that you have. We're quite actually stunned by that tool to represent and re-show, I would say recreate the scene of how the collapsed debris and the importance of that debris in coming to your conclusion in forensic engineering. I would say 2-3 things to my fellow participants here. I just want to read a little to you, Professor, if you allow, the famous, how did forensic engineering actually get formalized and start? You know, what we're dealing with today is forensic engineering, investigating collapse and then learning from failures so that they may not happen again. So how did it start? In 1847, the D Railroad Bridge, which was in cast iron and wrought iron, collapsed on the passage of a train few months after construction. It was built by a legendary engineer of that Victorian era called Robert Stephenson. So on examining that, what were the lessons learned about an investigation, which is followed till today, the practice that is followed even till today in forensic engineering, what Professor Calvi has been demonstrating to us, I'll just epitomize. An investigation was performed by a lead engineer who examined the site of failure and the debris and collected materials. He performed testing and analyses, reviewed witness statements, recreated events, recreated the collapse, recreated the whole event, then formulated a report attributing causation of the structural failure, which we just saw. And like modern investigations today, the failure analysis was not conclusive. It's nothing like 100% we are sure of. You know, there is some region of doubt still left. Was not conclusive, but was able to determine probable cause. So the probable cause, then the 30-ton trigger it. Did it fall? Did it not fall? We don't know, but we can postulate. So these are the lessons which are still followed today in forensic engineering. The process of it is still the same. So, of course, with that, we understood about fracture and fatigue and the whole idea of the decollapse in 1847. The lesson learned from that was to bring in the whole theory of fracture mechanics into bridge engineering. And then, of course, the understanding of fatigue and moving away from brittle cast iron and wrought iron to steel. So that's how important that collapse and the lessons learned from that were. Coming to the other way of looking at it, as we do in our task group, first response and preliminary assessment, development of investigation strategy, which is what you saw, fact gathering and document review, engineering analysis to determine causes and responsibilities, who is responsible, and reporting. So I think we saw all this from a set of postulates to coming down to a very narrow regime of where the possibility of failure lies, the reason, how it triggered, how it happened, and it still remains not 100% for a fact. It remains with a little uncertainty. Did the coil fall or not? We don't have pure evidence about it. So that's the unsure part. This is what I wanted to share with you. And you just, this presentation just is a classic modern day, super. Now, 2 things I want to ask, if I may. Why were acoustic emission tests not done to detect the voids? Because they're linear and they should have detected a large void and a linear element. And GPR is very small and compact. They could have been done. Now, if they weren't done, we don't need radiography, we don't need anything. This was sufficient to detect any void. Just asking, if it was done, it wasn't done at that time in 96 or whenever they did these investigations. The other moot point is of the towers that remained, the 2 towers that remained or the 1 tower that remained largely unscathed, the standing tower, there did we also go and detect these voids? Was any specific examination done at the 2 points where they could be released, either at the bottom of the stay or at the top of the stay, the failure mode and the twisting shear torsional mode? That could have been precipitated by either the break at the bottom or the break at the top. Those 2 points surely should have been investigated in the standing structure before it was blown up. This is just a question that would have been a huge lesson for us to have learned if it was done. And the last I want to ask you is about the practice in Italy. Worldwide, we address the differences in practice in forensic engineering. For example, in India, if there is death on a collapse, then we have a criminal procedure code, and there is death by negligence, and negligence will apply, then that invokes the criminal procedure code. But if there are no deaths, it can largely go by the civil procedures code, which there are no deaths and no, nobody's injured. Then we can invoke the civil procedure code. So they're two separate streams, and it's all written down law. And that practice is followed in India with maybe expert witnesses giving evidence. But what's the practice, say, in Italy or largely in Europe? Or, I know it is very different from the litigant type of approach which America adopts, the fixing responsibility in litigation, the litigious type of approach America adopts, and Europe has a different way, I would say. What about Italy? Is it some particular, you can talk to us about the way the forensic investigation and that was, the formalization, how it was done, the practice actually? Thank you. Thank you.
It's a pity that you decided also to ask a few questions, because your speech was the perfect conclusion of this this presentation. But for what concerned the two questions, the first one, yes, I agree. I agree now that that something might have been possible in terms of selecting the top and bottom, as you're saying, and so on and so forth. But let me very frankly answer a question with another question. And the point is, what should be the level of preparation of an engineer who is in charge of taking care of a network of freeway and bridges? So this is a very serious question, because the capacity of individuating the fact that you have to check this and that goes with a very high level of specialization, understanding, studying, and so on. And there are not so many engineers that would be able to take that decision and to give that suggestion before the collapse. Now is easier, but I always try to ask myself this kind of questions when I'm asked to be involved in a court case, that I try to avoid as much as possible. Actually, this comes to your second, well, which is more, it's not exactly a question, it's a point raised. I don't know if you know, Alok did not mention that, but at the time of the earthquake in L'Aquila, I was the head of the civil protection. Well, not the civil protection, the scientific body who was consulting for the prime minister and the civil protection. And after the earthquake, I was sued by a public prosecutor together with other 6 people. And we were at the first justice level condemned to 6 years of jail because of manslaughter. And then we were declared completely innocent at the second and third level of justice. But I tell you that to pass through this is not something that is not leaving a sign on yourself and on your family. And the reason for that was simply that, according to some public prosecutor, L'Aquila should have been evacuated before the earthquake because there had been some foreshock or something like that. I'm telling you this brief story to tell you that my relations with penal and civil law are quite difficult, and often I do not understand the way of reasoning. As you are saying, if a bridge collapses, if there is one person that dies, there is something. If there is not that person, there is something else. But from my point of view, the responsibility are the same. I mean, why should be because there was someone was passing? So I cannot answer your question. I simply say I do not fully understand all this, and I try to stay as far as I can from all this. My entire technical and professional life has not been dealing with try to avoid responsibility, but on the opposite. Actually, this is one of the faults. My wife blamed me because I take responsibility. You know, it's you always say, okay, it's my responsibility. So you understand that it's a delicate and difficult matter. I hope this is enough to comment.
Absolutely, absolutely. Thank you.
Thank you, Professor Kalvi. Now, our fourth panelist, Mr. I.K. Pandey, somehow he was present, but now I find that he's there. Maybe he is the Director General of Ministry of Transport, a very highest post in the ministry, and he is very busy person. So I am very thankful to him that he could find some time to attend, but he is not now here. So I see, may I request Dr. Visalakshi, who has introduced me in the beginning, to say a few words. Dr. Visalakshi, you are there? You can unmute, and let me introduce also Dr. Visalakshi is the professor of Mahindra University, Hyderabad, and she is the honorary secretary of our association. She is graduated from Osmania University, Hyderabad, and PhD from IIT Delhi. Dr. Visalakshi, would you like to say a few words?
Yes, Alok.
Yeah.
Yeah, thank you so much, Professor Kalvi. It was a wonderful lecture going through the forensic details of the bridge collapse, giving us the intrinsic details, how it has been done, and providing us with the reasons for how the collapse has been done. Okay, it was wonderful to go through your presentation, and we are privileged to host you on IS Truckee platform for such a wonderful presentation. Thank you so much.
Thank you,
And,
Dr. Visalakshi.
And I have one question, if I may, I have one question, Professor Kalvi. Can I go ahead?
Yeah, please.
Yeah, Professor Kalvi.
Please go ahead.
Yeah, so for this cable stay bridge design, okay, the stresses which are induced due to the torsion and the stresses which are induced due to the shear, okay, can we say that both are same, or else what could be the difference of these shear stresses which are being induced from these two phenomena?
I missed the first part of your question because of noise. Can you repeat the first part of your question? You said I got this phenomena, but what did you say before that?
Yeah, I was talking about the shear stresses which are induced because of the torsion in the bridge.
Yes.
Okay, and the normal shear stresses which are being induced.
No, the shear torsion in the deck. This is what you're asking. What was inducing the shear?
Yes.
No, yeah. Okay. No. That's very simple. If you imagine to release one of the stays, then the deck is hanging through only the stay on the other side. So you have a deck which is all on one side of the stay, and therefore you have torsion and you have in-plane bending moment. So you have a situation where this in-plane bending moment and this torsion is adding up to the normal condition in which you have vertical shear and bending moment in the vertical plane. But this comes from the release of the stay. If you don't release the stay, you do not have this problem. So this is not the cause of the failure. This is a consequence of the first point, which is the release of the stay. And if you allow me to say one more word on this, because I'm seeing there are so many people commenting, but it's impossible to respond to all of them. But one of the questions says the fall of the coil should have been included in the design. I do not believe that Morandi has included something like that back in the 60s. But the collapse of a coil like that would not have been inducing collapse without the loss of strength due to corrosion and so on. The fact that this coil weight was about 30 tons, but due to the flexibility of the deck and so on, the amplification factor was less than 10. And if you remember that in the state there were some 22 meganewton of force, the variation of force is not major. It's just a bit higher than the force that you have if you put a long column of track on the side. That's it.
Thank you, Professor Calvi. I think I will take 2 or 3 questions. We are now running short of time. I think we will take just 3 questions, if you permit me, Professor Calvi.
One I already picked up. Should I pick up them myself?
Yeah, kindly pick up yourself and you can answer
but
also.
One that was there, I pick it up. Another one is what could we do with corrosion? Well, I repeat again that corrosion up there was essentially due to bad detailing. We now know it and we can avoid that. I mean, I don't think that corrosion is a major problem today, that we know all the problems of penetration of water and so on, of the importance of injection of ducts and so on and so forth. So I think that this is something we have learned, and as Professor Tandon was underlining, this is not something that was in the common knowledge of the 50s and 60s. Today, if we know that there is a problem of corrosion, we can both take measure of protection. In some cases, as probably most people here know, it is even possible to use cathodic protection and so on and so forth. So there are several measures. Another question here is talking about the problem of corrosion in terms of corrosion, which is reducing the section entirely, and what is called peak corrosion, which is concentrated in little points. We have done a lot of analysis using most of the available models, combining these both effects of corrosion. And again, if we use the standard values that are recognized as possible over the years, the bridge would have been able to go for a much longer life. You know that probably the rate of corrosion, even in I mean, a uniform rate of corrosion could be in the range of something of I don't know, 0.05 millimeters per year, so on and so forth. There, things were much faster. I'm just going through to see. So I already mentioned that, I would already mention that the collapse or the falling of a coil like that from a bridge would not have been inducing collapse without a significant presence of local corrosion. No question about that. I think that's it. I mean, there are more comments than.
Okay, so we can conclude now. Let me.
Can I just ask one thing to Professor Calvi? Professor,
sure.
When do these reports that you have made come into the public domain? Do they become public domain material like the S-Cross type of confidential reporting and which you have in the UK and in other parts of the world? Would these reports become public domain available to others? I'm just asking, or are they kept fully confidential always?
For the time being, we have been allowed to produce papers to be published in journal and so on, and this will come out soon. And actually, I could even anticipate papers when we submit them to the journals. For what concerns detailed reports, I'm not yet allowed to make them public because, as you can imagine, the first phase of the court case will start probably this summer. Because up to now, they've only been working on evidence, on detecting evidence. And At a certain stage, I do not see why they should not become public. But for the time being, I cannot distribute them.
Right.
So we have come to the end of this fascinating webinar. I profusely thank Professor Kalvi for agreeing to, enrich our knowledge and inspiring us. This kind of, forensic investigative kind of webinars are extremely enriching for all of us. I also thank the participants who have actually attended in pretty large numbers. And I thank the panelists as well who have given their valuable insight. And I would look forward to Professor Kalvi. I would look forward to reading his papers on this subject. As he mentioned, 5 or 6 papers are about to come. And I would also look forward to having him here in our association online, or even in some, whenever he is in India. We would love to hear him and invite him in our association and have interaction with him, more closer interaction on physically. Thank you very much, sir, and all the best to you. Thank you. And with this, I close this session. Thank you.